Well, hi there, folks, and welcome to another session of ENGAA Demystified. Today we are looking at 2021 problem. It's from the Advanced Physics section, and the question reads as follows. The diagram shows a circuit containing two power supplies with negligible internal resistance and two resistors with resistors R and 5R. So negligible internal resistance, and the two resistors are labeled as R and 5R. Okay, the EMFs of the power supplies and the magnitude of the direction of the current in one part of the circuit are shown. One point in the circuit is labeled P. What is the magnitude of the current at P? Right, so just looking at this problem, they want us to work out the current going through P. So looking at this, we would be fair to probably say, of course, that the sense of direction of the current in our other loop that's not labeled would be going in that direction here to the right, like so. Right, so what are we going to have to apply here? Kirchhoff's laws. And we are going to be thinking firstly conservation of energy. We're going to think of each loop here. So let's think about the loop in blue. And we shall also have another loop in red. So we've got two loops we're going to be concerning ourselves with. Now, what does Kirchhoff's voltage law states? Well, quite simply, it simply states that the sum of the EMFs must equal to the sum of the drops in potential. In summing up the EMFs, the sense or the direction that the EMF points in is important. So my negative terminal I will be taking as the position of low potential, and my positive terminal here as higher potential. So my EMF arrow goes from low potential to high potential. Likewise, on the EMF for the 2 volt, that's my low potential, and that's my high potential, the positive terminal. So my arrow is pointing in a different sense. So one here will be given a positive and the other will be given a negative value. It doesn't matter which one, as long as we keep with that sense in direction. Now, given that the current is going in that direction through the resistor labeled R, my potential drop I will represent with my arrow going upwards, like so. Meaning the arrow always points to the place of, or the tip of the arrow points to the place of higher potential. So the sum of EMFs in this loop here, the sum of EMFs, we can give the 2 volts a negative value because it's pointing, or rather it's going in a clockwise sense, and the 6 volt potential is going, we'll call it positive, it's going in an anti-clockwise sense. So we can see that that's 6 minus 2, which is 4 volts. This must be equal to the sum of the potential, or the sum of the drops in potential difference. We've only got one resistor, so the drop there in potential must be 4 volts. So we can work out what that resistance is, R, using R equals V over I, and 4 divided by 10 times 10 to the minus 3, giving us a value of 400 ohms. This means here that our 5R resistor is actually going to be equal to 2000 ohms from 400 times 5, so 2000 ohms. So to work out the current in my red loop, I'll again apply Kirchhoff's law, and the sum of the EMFs, in this case there, sum of the EMFs is simply 6 volts. There's no other opposing battery or cell to reduce that or enhance that, so to speak. Okay, so 6 volts must be across 6 volts must be across that with a PD drop across 5R. So to find the current going through 5R, or the 2000 ohm, that would be V over R. Our V is 6 over 2000, 2 into 6, that's 3 there. So that gives us 3 times 10 to the minus 3, which is 3 milliamps. And to work out the current through P, here would use Kirchhoff's current law, which really comes from conservation of charge. And so we have a total of 10 plus 3 milliamps going into the node, sums up to 13 milliamps, giving us an answer of E. Hope you found that useful, and I wish you a lovely day, lovely time, whatever you may be doing, and hope this has helped in some form or shape. Have a good day now. Thank you. Bye.